So I'm sure you've come across scale drawings a lot in life, at least on maps, maybe. For example, say like I have a map of Uganda. The map is only, let's pretend it's 250 centimeters across. Does that mean that the country of Uganda is 250 centimeters across? No, it's a lot more than that. But the map is a scale drawing of the real object of the real country of Uganda, and so there's actually probably you've seen a scale like, for example, in this example, I would say maybe 1 centimeter is equal to 1 kilometer, something like that. That's the scale that shows how the shape on the piece of paper that we call a map corresponds to the shape of the country on the planet Earth. Or you might see, I don't know, like a scale drawing of, say, an airplane. Is the wingspan of the airplane really 6 inches across? No, it's a lot more. But the scale drawing is accurate because all the corresponding parts are proportional to the real object. So, um, really, a scale drawing, we would say, a is similar to the real object, and using similar in the special math way that we use that word. So it's not like, oh, it's sort of like the object, but actually the corresponding sides are proportional. So I have an example here that kind of, I hope, illustrates what I'm trying to say. Um, where let's pretend like I've got um, a rectangle here out in the quote unquote real world. It's 100 meters across. Pretend. Use your imagination. Thanks. It's 100 meters across. It's this large green rectangle. Nobody knows what it's for. It's just there. And it's 40 meters high. Okay. Well, pretend like I wanted to make a scale drawing of this rectangle because I wanted to teach this cool lesson. So here's my scale drawing, and I put little dotted lines here, so you know it's just a scale drawing. It's not the real object. Um, it's 10 meters across only and 4 meters high. Now, yeah, of course, I mean 10 meters across would be still quite large for a scale drawing, and you can't fit that on a piece of paper. But I'm doing that for the sake of simplicity. So here's my scale drawing, and here's the scale. What this is saying is 1 meter on this guy, the scale drawing, is equivalent to 10 meters in the real world. So this is 10 meters across, but really what that is representing is something that's 100 meters across. 10 times 10. So that's the scale, and I want to show you that these objects, the real object, the real rectangle, the mysterious green rectangle that nobody knows what it's for, and my scale drawing of it are similar figures. And yeah, so let me prove that. So uh, similar figures have corresponding sides that are proportional, which means the ratio of the corresponding sides are equivalent. They mean the same thing. So for example, if I look at this side, it's 10 meters across, and the side that correlates to that or corresponds to that is 100 meters. Okay, so I can reduce that ratio to, we divide both by 10, so 10 divided by 10 is 1, 100 divided by 10 is 10. So that's as far as I can reduce that. So that's the ratio of this side to this side. Well, if these are truly similar figures, then the ratio of this side to its corresponding side should have the same value when you reduce it. So we've got 4 meters. Oh, sorry, Mathceratops. I'm going to kind of get in your way there. Um, 4 meters to its corresponding side here is 40 meters. And we could reduce that, divide both by 4. Oh yeah, I'm getting good at drawing those little dividing, sort of. Not really. Those are kind of bad. 4 meters divided by 4 is 1. 40 divided by 4 is 10. So yeah, these ratios have the same value when you reduce them. So that means the corresponding sides are proportional. So these are similar figures. And actually, the ratio of the sides, the corresponding sides, 1 to 10, is the same thing as the scale, 1 to 10. So really, that's what the scale is. It's defining the proportionality between the corresponding sides. Awesome. What's this about? Unknown. Unknown. But scale drawings, now you understand them on a deeper level. So awesome job. You are becoming a total Mathceratops.